So today's speaker is Dr. Areeya Chantasri. Areeya did her PhD at the University of Rochester under the supervision of Professor Andrew Jordan. She graduated in 2016, after which she spent a couple of years as a research fellow at the Center for Quantum Dynamics in Brisbane. After that, Dr. Chantasri received a faculty position at the Department of Physics at the Mahidol University in Thailand. Areeya is an expert on quantum measurements, quantum control, and chaotic quantum dynamics. In her seminal Nature paper from 2014, Areeya, with collaborators, mapped out the optimal route between two quantum states in the presence of perturbations. Today, Dr. Areeya Chantasri will be telling us about her new work on mitigating random telegraph noise in solid-state qubits. So with that, Areeya, the virtual floor is yours. Thank you for coming.
Okay, thank you very much. That's a really thorough introduction ever that I've seen. So I would maybe start with sharing my screen. Is that okay? So that is this one. Yeah, you guys can see it. All good?
Yeah, all good.
Okay, sure. Okay. Thank you, David, for the introductions, and also thanks, David and Hugo, for inviting me to give this talk. So this talk would be about the mitigating the qubit dephasing from random telegraph noise using spectator qubits. So I would like to, I don't know, I hope that I can hear some of the noise interacting with me, because otherwise it will be it's like the same as like I'm talking to myself in front of the screen. So some noise would be helpful. You guys don't have to mute yourself. Okay.
We will sort that out. As soon as someone asks a question, there will be noise.
Yeah. Sure. Okay. All right. So this work has already been recently published in the PRA. So there's like these versions of the PRA letter. It's like shorter version, telling all the summaries of the main results, and then the more detail of the calculation will be in another PRA, like a joint publication. Both of them published just this year. So the collaborators here, like 5 of us. So this is like, well, most of all of us at some point were at Griffith University, and then some of them, including me, has left to Mahidol. And so we worked together with Howard Wiseman. Howard Wiseman was the principal investigator. So he came up with the idea, and then we try to work out all the detail. Okay, so a little bit on myself, and also a researcher in Thailand. So I came from Thailand, and so after I worked in Australia for a while, I went back to Thailand and then start a theory group over there. And then if you haven't seen quantum physicists from Thailand before, I'm one of them. And actually we have like a few of people, actually, not a few, like up to 100 people working in different fields in quantum technology. So like quantum simulation, quantum cryptography, communication, sensing, and also like quantum information theory as well. Okay, so a little bit of background on this. So why do we need to care about the noise mitigation? Because qubits are actually interacting, or quantum systems are interacting with the environment and interact with the noise all the time. And then in order to do something useful, to get like the quantum system to do something useful, like quantum computing or quantum metrology, we need to deal with all kinds of noise that are affecting it. And it could be like noise that comes from classical fields or like quantum fields. It could also just be like a vacuum state of like infinite path that cause something called spontaneous emission, for example. So the coherence process for qubits, I can kind of separate into two main ones. One is a spontaneous emission, which is like the decay of like side-to-state to ground state. And then it can describe by like T1 coherence term, or the dephasing process, where the phase of the qubit get kicked around randomly. And then the phase, like on average, it is becoming the decay of the qubit off-diagonal elements. So in this talk, I'm going to focus on the noise that cause the dephasing on the qubit, and then how to get rid of that kind of noise using the spectator idea. Okay, so a little bit on the motivation on the experimental side is that we looked at things called solid state qubits. So solid state qubits, including things that can be made by like quantum dots, where you have like gates and substrates, and then it could be electrons hopping in and out between different dots, and then that make the qubits. And also it could have like different structure of the quantum dots as well. And then in this picture down here is the phosphorus donor, or like you think about the phosphorus atoms inside a silicon substrate. And it also includes things like trans 1 qubit superconducting qubits that was done from like the IBM or Google, right? So why do I care about these solid state qubits? Because if you look at qubits, it has a lot of like environment all around. You cannot get rid of these atoms in a substrate, and different atoms has nucleus, it has electrons, it has different kinds of like noise that can affect your qubit. So in terms of solid state qubits, there are a lot of noise that can affect the qubits, and some of the noise it's hard to remove as well. So as an example of noise, one is like nuclear spins. Like difference of other atoms on a substrate has nucleus, right? And it has like different spins, and it can affect the qubits that actually in that substrate. So that's also difficult. It also can be things like electrical noise. For example, electrons hopping around in a substrate, like charge noise, electrons can get trapped in some of the location and then like fly away at some point, hop in and out, that kind of thing. And that results in things like 1OF noise, or the noise that occur in the low frequency. So we're going to focus in this kind of low frequency noise or charge noise, where the environment has electrons can hop in and out, and then that affect the data qubits that we're interested in. So in this case, so it's like a regime that we are interested in, like having like qubits that we're going to call it data qubit, which is like qubits that is can do something useful for example, like data processing or anything on the metrology problems and so on. And then these qubits are affected by noise from the environment. But then how can we correct the noise on these qubits? We have to measure the noise and then see how it evolves in time, right? And so the idea that we propose is that using the spectator qubit. So the spectator comes from the idea of like spectator in terms of sport. You look at the games and then see how the games is moving in time or evolving in time in a sense, right? So in this case, the spectator qubit is used to probing how the noise is behaving in time, and then hopefully we can measure this spectator also in time to get the information of the noise. Okay, so that's the idea. And why do we interested in it is because it can maybe better, or in some regime at least, it can be better than the quantum error corrections, where you probably know that quantum corrections could have it needs the physical qubits that kind of encoding one logical qubit. It can have like 3 qubits or 5 qubits or 7 qubits, depending on what kind of error correction codes that you need. But it all needs a large overhead of the extra qubits in order to do the error correction. And so we don't want that. We hope that in this case, we're just going to use like one spectator qubit or maybe a few to probe different kinds of noise that can affect the system. Okay. And then another hope
I have a
that
question here,
yeah,
Areeya.
go ahead.
It's
Go ahead.
actually two
Yeah.
questions. So someone from the audience asks, is the spectator qubit exactly the same as the other qubits?
It doesn't have to be. Yeah.
Okay, that's the first question. I'll let you answer that. And then the second question, which you can answer as well, is this a form of quantum error correction?
Is this a form of quantum correction? Okay, this is kind of definition kind of word, right? So there are in the field, people takes the word of quantum error correction in different ways. In the past, as far as I understand, they still use the word quantum error correction, so QEC, in the sense of you have to find a code, for example, like a 3-qubit code or 5-qubit codes, 7-qubit code to correct a different kinds of the error. So, but if you want to use the QEC or quantum error correction in a general sense, then this is some kind of error correction. It's like if you translate it like words by word, it's just the way to correct the error on the qubit. So I hope that answered the question. So it depends on the terminology in the field. So
Yeah,
it
I think
is
that's
for
good.
me. Yeah.
And
For
you
me,
said
it
that,
is. Yeah.
you said that the spectator qubit doesn't have to be the same as the other qubits.
Right. So I think the important part is we need to know how this spectator qubit interact with the noise. That's more important than saying that this one has to be the same, because the goal of this is to get these qubit to probe the noise. So as long as it's probe the noise, as long as it's sense the noise, and you know the dynamic of it, and then you know how it will evolve in time, and then you know how to measure it, and then how to analyze the measurement readout, then you can use the readout to kind of refer back to the noise. So that's the goal, is to estimate the noise and then use the noise to calculate the error in the data qubit. So as long as you know all that connections or the relation between them, it is okay. It doesn't have to be perfectly the same.
And there seems to be
Does
a follow-up question, which is,
Yeah,
does
go
the
ahead.
spectator qubit have to be a qubit, or can it be a classical sensor?
It can be classical sensor. Good question. So if the noise is large enough that your classical sensor can sense it, then fine. Yes, you can just use the classical sensor to anything that can sense the noise. And that's like classical error correction, right? But if let's say that the noise is maybe smaller or is harder to measure by any classical sensor, then you would have to use the quantum sensor in a sense, right? And then now when we go down to the quantum sensor, what kind of quantum sensor, right? Does it have to be qubit? No, because actually there's like work by Ash Clark just recently following our work. They look at the spectator qubit the same similar way that we are doing, but then they're looking at the cavity or like a continuous variable instead of just qubit. So it definitely can be qubit. It can be any other quantum system. Yeah.
I have a follow-up question as well.
Go ahead.
So are you assuming, or do you have to assume, that the noise is correlated between all data qubits and the spectator as well?
That's right. That's the important part. So that's why I'm looking at this diagram. You have to assume that the data qubit and the spectator qubit sense the same noise, or at least the noise are correlated, because otherwise it will be useless, right? That if this spectator would just sense a different noise that affect the data qubits, then like, yeah, you cannot do the correction.
And in reality, is this an assumption that is allowed? Can you make this? Or...
So this is like one of the good, we thought about this as well. And that's why we can look at the solid state qubit case. So let's say that like on the substrate, there is like electron hopping in and out somewhere on the substrate. And then we maybe have one qubit staying here and then another qubit staying closer to the locations of the noise. Then these two can affect, well, with the Coulomb interactions, right? It can affect the same noise, but different distance. And so in a sense that, yeah, that my answer is yes, it can happen in this regime, for example.
Okay, thanks.
But it can be more general in that it might be other kind of process that the noise can affect both data qubit and the spectator qubit, not like highly correlated, but maybe somewhat correlated. And that is like a different directions that we kind of go into as well. But let's say that this work, we'll just go with something simple for now, that all the noise are the same, that affecting the data qubit and the spectator qubit.
Okay,
that's all good. Yeah, okay. Okay, so that will lead to actually this bullet point as well. So this bullet point, I kind of want to add that our protocol that I'm going to show you later on is actually works even if you don't have the data qubit. It's like, why do we need to care about if we don't have the data qubit? So it is when, if we want to just monitoring or measuring the noise alone, we want to know like how the noise is evolving in time. And then in that case, we just need like the spectator qubit that can probe the noise and then measure, and probe the noise and measure in time, and then use the data from the measuring the spectator qubit to estimate the noise in time. So in that case, we don't need a data qubit, so we just use the spectator. And then interestingly, this idea has already been done, or in the sense that it is similar to atomic clock experiment. So in the sense that in atomic clock experiments, you have the laser that has a frequency that you want to stabilize into one fixed frequency, right? Because you want to use that laser to be like the clock ticking. So you want the frequency to be fixed. But then in reality, the frequency of the laser is fluctuating in time. And so what people do in experiment in atomic clock is they use atom, right, as some kind of spectator qubit in the sense. For example, using a cesium atom to couple with the laser, and then measuring the populations of the atoms, and then use that information to estimate how the frequency change in time, and then do the feedback to correct that shift of the frequency to kind of stabilize the laser. So this is something that I just recently talking to some of the theories in atomic clock experiments, and I'm like, okay, well, this is like really similar. And so definitely my theory analysis can be used for that case as well. Okay, so now what's the protocol and why is it interesting? And then I will show you that it seems simple, but it turns out it's not trivial at all. So the protocol is we have some kind of noise that change in time. It has fluctuation, it is unknown, and you want to know how it changes in time. We can have things like a spectator qubit that can sense this noise in time, right? It evolves with the noise realization. And then what we can do is to measure it, right? So we want to measure, so in this case, we focus on projective measurement. Well, it could do the continuous measurement, but there's another problem. So we do the projective measurement. So whenever we probe it for some time, we do the measurement on it and get an outcome. If it's in qubit, then the outcome would just be 0 and 1, right? Just like a binary number. And then if it we can let it evolve for another time and then do the measurement again, and then also, and so on and so on. And so with the measurement readout 1, 2, and so on, we can use these data of the readout to do the estimation of the noise And then if you want to, if we have the data qubits, then we can use that information of the noise to do the correction on the data qubit. Okay, so in this case, we hope that we will be able to use the measurement readout to estimate the phase or the state, let's say in general, the state of the data qubit as close as possible to the real one. Okay, so oops, sorry. This one.
Quick interruption again.
Yeah, go ahead.
So if you're making many projective measurements on the spectator qubit, how are you making sure that you don't have quantum Zeno effects changing where your state will be compared to the data qubits?
Good point. So the Zeno effect would occur when you measure it too fast or like fast enough that you would just kind of freeze the state to one state, right? So that's kind of the Zeno effect.
Yeah.
But I don't think in this case would
it's not
be
that fast.
in that regime. It's not that fast because the thing is, if you make it too fast, like you say, you would just freeze the qubit and then you won't know anything about the noise.
Yeah.
So that's not a good regime.
Okay.
And so we have to wait for some time. That's why like there's like something called a waiting time for the state of the spectator to accumulate some kind of information of the noise before you do the measurement.
So there's a sweet spot in measurement frequency where you don't want it to be too fast nor too slow.
Right. Okay. That's right. And that becomes a really like non-trivial problem to find the sweet spot. Yeah.
I guess this is related to another question that's in the chat now. So why is it better to measure it many times and not just once?
Because the noise change in time. That's it. So if you measure it here, you would just get the information at that point. So another thing is because the qubit, let's say that, well, qubit is moving in a sense of it rotation, right? There's a rotation around the Bloch sphere, for example. And then if your noise has accumulated for some times and then your states just like rotates multiple times, and then you will lose the information from that like periodicity of the phase. So you will lose like, okay, when it's like positive one or when it's a negative one if you wait it too long until the end. Does that make sense?
Is it that like you accumulate the phase and that will wrap around 2 pi, and then like if you wait for too long, you're gonna lose
the information in between.
I also suppose that if you only measure it once at the end and you only have one spectator qubit, you just get a 0 or a 1. So
yeah,
it does. I guess
true. That's a good point. Is that gonna be the same? So that would just like be one bit of information, and that doesn't help much. It's better to do like, if you think about, well, actually it's a good point, like thinking of it, if you want to know that the evolution of the noise in time, or if you want to know how, well, actually I should say that the effect of the noise on qubits or quantum system, usually it is some kind of accumulated effect. It's not like the noise here will just tell me what's the state of the qubit at that time. No, you have to get all the history of the noise up until that time to tell the information or the state of the qubit or the state of the quantum system. So you can see that there is like a history kind of information up until that point that is important. You cannot just like do one and then tells everything about the past. You have to do multiple times in the past to be able to track something better. And then you would hope, well, you could just guess that if you want to get the perfect evolution of the noise, you would just do it fast enough, right? That you would just like take a picture of how the noise is evolving in time every second, right? So that is, in the classical sense, yes, that's what you want to do, is to do it fast enough to see what's the evolution of it. But then now going back to like Hugo's question is you cannot do that with a quantum sensor because quantum sensors need some kind of delay time to pick up that information. And so that's like a difficulty between doing too fast or doing too slow. Does that make sense?
Yeah, I think that makes sense. There is a
Yeah.
follow-up question.
Yeah.
It says, so the noise canceling itself could happen on a real axis, but not on a circle. So I'm not sure if I fully understand, but maybe you understand that question, Areeya.
The real axis, but not on the circle. I'm not sure what the real axis in this case means. Maybe they can explain a bit more on the question.
Yeah, I will let you know if they maybe write a bit more in the chat.
Okay. Should I proceed?
Yeah, let's proceed.
Okay. All right. So hopefully the protocol makes sense so far. And here is the questions that I would like to ask, which is related to some of the questions that has already been asked. Like how does it work? What kind of noise that it work well? And what kind of regime that it works? What kind of optimal measurement or optimal control that we should do to get like the best something out of it? And then how does it perform? And then in this case, we want to know when to measure and how to measure. Like it's actually related to one of the questions say that can we just do one measurement and instead of like many? And then I think later in my talk can also answer that question. It's like how many measurements we want to do and then when and how. And also the measurement observable as well. We want to optimize over that as well. Okay, so just to make problem simpler a bit, we're gonna focus on the low frequency noise. So in this case, we're gonna model the low frequency noise as a two-state fluctuators. So in this case, it's a random telegraph process. So it fluctuates between two values. In this case, it's just +1 and -1. So it jumps between +1 and -1, and then try to find the ultimate performance of that. Okay, so excuse me. So let's do the math a little bit. So the math here is a noise. We're gonna call it beta as the RTP noise, fluctuate between +1 and -1. And then there's a jump rate, which means that if I stay at 1, what's the rate of jump from 1 to -1? And what's the rate of jump from -1 to 1? So that's defined by the gamma. And so here's a Hamiltonian of the qubit. So this is just like kind of model that we want to set so that we can solve it. But actually you can generalize it to different Hamiltonians or more complex Hamiltonian. So this Hamiltonian is, as you can see, it's just the frequency of the qubit is modulated by the noise. So the beta is multiplied in front of the sigma z, which is in this case just like the frequency of the qubit, right? And so the beta will determine how the angle of the qubit is evolving in time, whether it's going to go in a positive way with some rate or in a negative way with some rate. So the rate is defined by the kappa. This kappa is like kappa D is a kind of sensitivity of the noise of the data qubit. How the data qubit is sensing the noise. If kappa is large, then it kind of fluctuates fast, right? Because of the kappa. And then kappa S would be the sensitivity of the spectator qubit. Okay, so then the phase of these two will just can be calculated by the kappa D multiplied by the X. What's in X? As it's just the integral of the beta, right? Because you have the Hamiltonian here, is just the phase is just the integral of that. So it would depend on the X, which is called the integral of the beta. I'm going to call this accumulated noise. So with beta, I'm going to call it noise, and then X, I'm going to call it accumulated noise. So you can see that this one, it depends on the history of all the noise from time 0 to any time t, right? And that's why it's difficult. Also, the spectator qubit also depends on the kappa S, which is different, and then the X as well, the accumulated phase. And we're going to measure this spectator qubit at some point in time with some observable. In this case, it's just a Pauli observable, defined by the angle theta. It doesn't have to be X, it doesn't have to be Y. It can be X plus Y, for example, with the angle theta. So this picture is just like the evolution in the XY plane, just to make it clear, because the Hamiltonian is in the sigma side, and so it's a rotation in the XY plane. And the measurement result is just 1 and 0. Okay, so a little bit more detail on this, just to make the math a little bit easier, is that every time we measure the spectator, we're gonna reset it. So think of it as spectator is probing the noise for some time, and then the measure here, get a result 1 or 0, and then we reset it to maybe like phase 0, and then let it evolve for another time, and then measure and reset, and then wait for another time and measure. Okay. And then the parameter regimes that we're interested in is when the sensitivity of the spectator qubit is larger than the sensitivity of the data qubit, which is what you want, right? Because we want to protect the error on the data qubits. You want this one to be smaller than the spectator, and you want the spectator to sense the noise faster. Okay. And here, just to say that the time is long enough, means that we can make the measurement on the spectator qubit many times to track the evolution of the noise. Okay, so hopefully you can still stay with me, and then you will see that why it is difficult. So there are a lot of parameters in the problem. Like, okay, there is measurement times where it can be many, it can be 1, it can be 2, or multiple times. And the time is like T1, T2 is also variable. It can, and then another parameter is the waiting time. So the waiting time is a difference between the 2 consecutive time. So like Tj minus Tj minus 1. Okay. And the measurement angle is also a variable. You could choose the theta to be anything. And then the measurement readout is like 1, which could be 1 or 0. And the value of the noise, beta, at that time, at the measurement time, we're going to call it beta 1, beta 2, and so on. And accumulated noise X also at the same time. Okay, so how are we going to solve this? We have unknowns, we have measurement. The idea is to use the Bayesian. Okay, so in the estimation theory, estimation theory, many people prefer things like Bayesian estimator, and then we are also those people. So we start with constructing the probability, all kinds of probability that we can have, and then use that to do the estimation. So we start with things like probability of the noise. So probability of the noise at the initial time, it would just be kind of prior information or prior knowledge of the noise, whether you think or you believe that is like +1 or -1 at initial time. And if you don't believe in anything, you think that is have no knowledge about it, then you would just assign it's like half-half, right? Like there's 2 values, +1 and -1. You just say, okay, it's like half-half probability. And once you have that, you can calculate the probability of beta at T1, and then accumulated noise at T1 as well, given the noise at time 0. So these can be solved by like master equation. If you have the model of the noise, Gaussian noise, RTP noise, or different kinds of noise, you can solve it, and then some of the noise you can solve it analytically. Okay, so, and then this is also another interesting quantity, is when you know the accumulated noise, and then you know the measurement angle, and if you know the measurement time or the waiting time, then you can calculate the phase, right? How the phase is evolving of the spectator. Then you can calculate the probability of the readout, whether it is 0 or 1, what's the probability of 0 and what's the probability of 1. And then you can construct this function as well. And then you keep going, doing like T1, T2, T3, and so on, and up until Tn. And then hopefully at the end, you can construct something that looks like this, which is the probability of accumulated noise. And this is what you want, right? Because so here is a the accumulated noise at the final time, and that can determine what's the phase of the data qubit that you want to estimate. Right? So that is like the final kind of holy grail that you want to calculate. And this one would depend on what the measurement readout that you get, and also the measurement angle that you choose, and also the measurement time. Okay, so hopefully up until now, the math is not crazy yet, because it's gonna get even kind of hopefully not too bad. So how can we try to find the base data and then the measurement time? So we have to come up with what is called cost function, right? In the estimation. So we need the cost function first. So we're gonna choose the cost function to be something we probably already care about, which is like decoherence. We want to minimize the decoherence on the data qubit. So the coherence is defined by just like 1 minus coherence. So the coherence is simply the average of the phase over like multiple realizations of the noise. And so if there's no noise, right, you can expect that this term would just be 1, right? Like e to the minus I5, e to the I5, which is absolute value of it would be 1. And then the coherence would be 0. But then if there's a noise and then the phase just go like uniformly distributed, then on average would just be 0. Coherence will be 0, and the coherence would just be 1, right? So then we construct these D with these e to the I phi d, and then as you probably remember, e to the I phi d is just the kappa d times the accumulated noise at that final time, xn in this case. And so the probability of the noise is something that I kind of construct in the previous page, like a lot of products of beta and then x and then theta and then delta t and so on. So I'm not going to go into details of how to construct this. It's kind of messy. And then there's a lot of integral over the noise, and then the sum over all the beta, like being +1 and -1. But the interesting part is all this complication, somehow after 3 pages of calculation, it becomes something that looks really, really simple. I mean, I came up with this math, and so you probably can tell that I'm so excited about it. Hopefully you are convinced that it's beautiful. So all this convolution becomes just a matrix multiplication. And then what matrix multiplication is just like kind of, well, here's a vector multiplied by some kind of matrix. And I'm gonna tell you what's the different A. So A is like a 2x1 vector. And then each of them, each of the element tells me the coherence of the data qubit, conditioning on what you believe as the beta, or conditioning on like what's the value of the beta, being +1 or -1. Okay, and then this A can be updated. Well, you can think of it as the kind of the Bayesian update by multiply with the F matrices. And F matrices depends on what? Depends on the measurement angle theta that you choose for that particular measurement, the measurement waiting time, how long you wait to measure, and then the measurement readout R, which can be like 0 and 1, right? And then if you make the measurement many times, you just multiply the matrix together until the end, and then you get things that I can call like an AN. So A can be updated from A0, multiply 1 time, we get A1, and then A2, A3, A4, and so on. Okay, and then we can calculate the decoherence at that time. So if you're interested in how we can do from the pink box to the green box, then you can go into our paper. Hopefully you guys are okay up to now. Okay, so if there's no question yet, I'm going to go deeper into how we can use these maps to calculate the coherence of the data qubit. So here's like how the map works. So we have the vectors and then matrices, and the matrix will depends on the measurement readout, right? Like we measure the spectator qubit one time and we get the outcome 0 or 1. And so we can separate the cases into 2. And then if you measure it 2 times, then we get 4 values, and then 3 times will be 8, and it will be 2 to the power of j if you do measurement j times. So counting all possible cases. So we're going to use these to try to come up with the best way to measure. Okay, I'm going to go through it a little bit by saying that A is actually really important, because A includes all the information about the noise, the phase, and also the probability of the readout. For example, if I have A at sometime J, and I can find the argument of this function, and then try to calculate, it gives me the estimate of the phase of the data qubit. So you just have to believe me that it is possible. Okay, and then also A can tell me the best guess of the noise beta, whether it's like positive or negative one. And then the A can be used to calculate 2 parameters that are the most important in this work. So one I'm going to call it zeta, and then one I'm going to call alpha. You don't have to care about it. Let's think of it as just some 2 parameters that tells me about all the information of the noise. Okay, so zeta and alpha, that's it. So I can do the calculation showing, okay, here's how I can look at some kind of phase space. Once we have these values, we can look at the phase space of it. And then, for example, we have the measurement at various random times, 0.8, 1.0, and so on. And I pick the measurement angle to be some kind of random number. And then I can calculate the theta and alpha to be, like for this case is T1, and for T2, it will be 2 values. For T3, it will be 4, and then T4 will be 8 points, something like that. Okay, but why it is useful? Sorry. So this one is going to be used to calculate the coherence. So if you remember all that math that I showed you in like 5 pages before, you can use these values to calculate the coherence over time. So in this case, this line is just the case without the measurement. And so here is the decoherence with the measurement. So here is like the measurement one time. And if you do more, you get different decoherence. And then you can see that the rate of the decoherence is actually decreasing with the measurement and the correction. So that gives us like the idea that, okay, here's why is it useful? It is actually useful because you can do the measurement and get information about the phase, and then do the corrections on the data qubit, and then improving the data coherence. Okay, I haven't done any optimization. It's already helping, right? So the question is, can we do better? How's the time going? What's the time that I have left?
I was going to say there was just a question about how do you optimize this, and I think you have about 10 minutes left.
Okay, sure.
Yeah.
So yeah, that's okay, good. So hopefully I can convince that we can try to optimize the delta T and theta here. So I can do maybe not too much in detail, but let's say that this is the idea that comes from Hellstrom quantum state discrimination. So if you think about this in like the phase of the spectator qubit, right? So the phase is evolving in time depending on whether the beta is in +1 or -1. So if it is +1, it move up, and -1, it move down, right? So if let's say that if beta doesn't change, and then the phase would just either going up or either going down, you would say, oh, we just wait until it goes somewhere at the top of like this point y plus y and then -y, and then do the measurement in like a pi/2 basis, and then you can separate between the top one and the bottom one, and then you know the beta at that point, right? But then it turns out that if you waited too long, then it's not good, because sometimes like the beta will just flip over time as well. You cannot just keep waiting. So there should be some kind of optimal time as well. So the phase is equal to the rate of the kappa s and then multiply by the time, right? This is just a calculation that just in the case if beta doesn't change. So this is the value. So you want to wait for some time, and then maybe the phase is somewhere here, and then do the measurement. So the question is, can you do the pi/2? Yeah, you can do that, and I'll show you that what's the result. But you could do better by doing the adaptive strategy. So the adaptive strategy is when, if you have the information about the beta from whatever the Bayesian update in the past, and then you have the likelihood of beta being maybe +1, and then you want to measure along this line instead of like pi/2, because that one will correspond to the optimal measurement or the optimal way to do the state discrimination between the top one and the one down here. So you want to do either positive or negative kappa s times the delta t. Okay, so let's say that there's like two strategy that I'm gonna consider now. Okay, so I'm gonna do like numerical simulation of some random parameters using non-adaptive case, theta being pi/2, and then the adaptive case where the sign positive or negative depends on my knowledge of the beta. Okay, and then the value of the theta, I'll just pick it randomly. I don't want to optimize yet. I'm gonna do it later. Let's say that I don't do it yet. I'll just pick it to be 1.0. Is a random number, and then I can show that. So here's the result. If there's no measurement, the decoherence increase over time as expected. With the measurement theta pi/2, here's a measurement T1, T2, T3, T4, and so on. The decoherence rate decrease as expected. And then if you do adaptive, even if you pick like theta to be some random number 1.0, then you can get better decoherence reduction. Okay, so now the question is how we can do even better, and that is like the protocol that we're gonna call MOAAAR. It comes from map-based optimized adaptive algorithm for asymptotic regime. So this is like the huge line of math, how we get to the optimal, well, hopefully optimal. We did not prove it is optimal, but we find it is like the best we can find. So we get these from looking at the phase space. Like I have been showing the phase space for some time. Why is it useful? So the phase space looks like something similar to the attractor. So if you work in the regimes of like the chaotic problems or some kind of fixed point problem, so if you do the measurement for sometimes the states kind of collapse to some fixed point, and so let's say that in this case I do like 1, 2, 3, 4, maybe 4 measurements. I get to the stable state, and then once you get to the stable state, you can kind of stay there for some time, and then we find that we can calculate the stable state or this fixed point analytically. And here's the result of our math, and ensure that the coherence is some kind of function of theta. And then the theta at this function at here is like some complicated function of theta. And then you probably can guess what I'm going to do next is to find the theta that minimize this function. And then here is the result of h theta, and then how it can, well, it has some kind of, I don't know, like, well, some kind of value function, and we can find that the optimal point is here, which is the values of 1.50055. It is not pi on 2. This is the interesting part that we find. It is close to pi on 2, but it is not exactly pi on 2. It's like somewhere around at the top of y-axis. And so we look at the phase space diagram, we check the stable fixed point, it works, and we can calculate the decoherence and then double check the results. And then we show that, so here's the kind of the zoom in from the previous picture. So this is the decoherence of what the no control or no measurement at all. The red one is the measurement when the angle is pi on 2. So it's actually reduced already. And then the blue one is the adaptive one with like random number of theta being 1.0. And then you can see that it's much better with the theta being 1.50055. And then there's 2 lines here because one is the approximation, the analytical approximation, and then another one is like the exact numerical values. So here's the answer to your questions on like how we get to the optimal. Well, we hope that it's optimal. We kind of like looking at like different kind of different clues in the math that we see, and then we try to find a way to optimize different functions, and then we get to the best we can find for the measurement angle here. And the decoherence become something that looks in terms of this function. As you can see, it's the functions of like 1 over kappa s squared, which tells you that, well, you can reduce the effect of the decoherence even further if you make the kappa s larger, right? So that's like the cool thing that we found. Okay, I guess that's like wrap up with my conclusion. I told you about the spectator qubit paradigm and then how it can be used to track the noise, and what, like, how many parameters that we have to kind of calculate and then include in the problem. And then we show that with a random telegraph noise, yes, it works well. We can reduce the decoherence rate quite significantly with the measurement on the spectator qubit. And then with the regime that we're interested in, it works. And then we came up with the MOAAAR algorithm, which is like the value of theta being 1.50055, and then it has to be adaptively picked between +1 and -1, depending on the values of probability of the noise that you know. I think that should conclude my talk. A little bit on the future work on this. There are a lot of things that I want to do, and then some of them has already been done. For example, we look at how if the parameters in the problem has some kind of uncertainty, and can our protocol still work, and when it's going to break down, because if it is going to be done in experiments, we have to analyze all that kind of uncertainty. And also if they're like the extra noise, like different kind of decoherence that we have, we cannot track what we should do, and in that sense. And I think other than that, it's just like trying to prove the optimal control. This is actually the discussions that David and I had when we were in Santa Barbara, and I think we have Me and Man Kai-sang at NUS, I think we have some idea of what to do with this, and a little bit on the experimental demonstration. I think I will stop at this point.
Thank you, Areeya, for a great talk. I can see we
Thank
already
you.
have some concluding questions in the chat. So I will start with the first one from an anonymous attendee. What about other types of noise? Here the vectors were 1D vectors and the matrices D times D with D equals 2 number of values of noise. How does this scale with the dimensionality? What about continuous noise?
Good, really, really good. Yes, so in this case, it's the 2, the matrix 2 comes from exactly the number of noise that can happen, like plus 1 and minus 1. Yeah, let me just go to that point. Okay, here. So this dimensional 2, because we are talking about the RTP, which has 2 values, and that's correct. And then now, if it can be expand into different types of noise, for example, different levels, like 5 levels or 6 levels, you will just expand the matrices, right? But the thing is, multiplying matrices with at least like maybe dimension 10 is still okay, because this one we just like multiplying maybe 5 times or 6 times. It's not that the scaling is not that bad. It's like it would depend on how many times that you do the measurement on the spectator qubit, right? Okay, so that's one answer. So now the continuous version, the continuous noise, it can also be done. And it's actually easier, surprisingly, because it will be something like multiplying the matrices. You can think of it as some kind of integral. So you can do, instead of multiplying the matrix, you would just do the integral of some functional in that sense. So we start doing or exploring things like a Gaussian white noise for some time, for some simple cases, and then also the OU process as another example as well. Yeah.
Okay, thanks, Areeya. And there's a question from one of the PhD students as well. What happens if the noise is entangling? Could measuring the spectator qubit potentially corrupt the computational qubits?
The noise is entangling. I'm guessing that entangling in the sense of it entangle with something else.
I suppose that maybe they mean that if you have your spectator qubit here and your data qubit here, and there is some unwanted interaction that entangles the two. And then if you're continuously measuring the spectator qubit, I guess you would
affect the others. Okay,
yeah.
okay, I see. Yes, it will be really hard. Definitely the entanglement between the spectator and data qubit, it's going to make the problem harder. I haven't explored that yet in any detail, but I think it will. Well, at least these protocols will not work in that case, and we will have to include things like we will have to include things like the state, well, like the space of the state would just be the space of 2 qubits, like data qubit and spectator qubit in the same, like, well, we have to include both subspace, right? And then the Hilbert space will be huge, will be bigger, and we have to look at the evolutions of both of them at the same time now.
Thanks.
I think that's possible, but it's going to be difficult. Yeah.
I think Crispin has potentially a final concluding question.
Yeah.
Yes. So with random telegraph noise, so the time scale for switching on and off, I mean, we measured that many years ago, all the way up into the gigahertz.
Mm-hmm.
You know, sometimes you can find random telegraph signal that's sort of a day, you know, you come back the following day and it's suddenly switched. I mean, is there a time scale on which your formalism can respond, or is there does that time scale matter?
So that time scale would determine the decoherence, or that's one answer. But also the time scale, or I think so. So the time scale that you talked about is this gamma. So this gamma will be like the switching rate, right? So the switching rate could be a day, like you said. It takes a day to switch, or it switches faster than that. So once we have these gamma, we would use these to pick or choose the sensitivity of the spectator that can be used to track the noise. So like think of it as just like, okay, if your noise doesn't change so much, then you can probe it slower with a slower rate, right? Your qubit will just send it slower. You don't want it to be too fast, right? You just let it, the kappa to be small, and so it slowly pick up the phase, and then you do measurement at some point. So the gamma would determine the sensitivity.
Right, but you're saying that there's kind of a fixed rate, but I mean it's still stochastic, right? You still got
yes
all time scales.
That's right.
Okay, and the other thing that we used to see is that it was rare that you would just have one random telegraph signal. There could be several operating at the same time.
Yes.
Have you've considered that by the looks?
Yes. So that is another project that we are doing. I think I can tell you a little bit more about it. So I don't have the slide here, but if you have a multiple RTP, multiple random telegraph noise, let's say that you have 3, right? And then so let's say that each of them can be +1 and -1, +1 and -1, +1 and -1. So at one time you could have, is that 6 values of the noise? Am I correct? Yes. So you count all the possibilities of how they can add up. Like if you get minus, you get -3. If you get plus, you get +3. So you can model it as a multiple level of noise if you have multiple RTPs. And this can be generalized to like different values of RTP, and then you just model it as like a different level of noise, like 6 level of noise, or 8 or 10, and then you will I think it's related to one questions where it will just change the matrix A and F. So the matrix A would just be 6 by the 6 by 1, right? The vector 6, and the matrix F would just be 6 by 6, something like that. Is that answer your question? Yeah.
Yeah. That's cool.
Yeah. So we hope that we will get some results soon, but I can say that the that generalization can be done quite easily on the math.
Yeah, I guess ideally they wouldn't be present at all, and we spent a long time trying to find ways of getting rid of them. And one of the ways was to put a bias on the gates, and as you cooled it down, and that had a you should speak to the experimentalists. It would.
Can you say a little bit more why the bias gates can help with that?
I mean, it's called biased cool down. So you either a positive or a negative potential on your surface gates as you're cooling down, and then basically you find that because the charge configurations are all changing as you're cooling down, you find that you kind of take them out of the regime where they can operate. Doesn't always happen, but I think there was a certain sort of element of being able to kind of suck that mobile charge out of the region of your device during the cool down process, because
Mhm.
once the system is cold, the charge can't, it can jump from one place to another. But if during the process of cooling it down, you manage to get rid of them all, this
Okay.
is not, this is like from 20 years ago that people
Right.
doing this. So I'm sure that your experimentalists know all about how to do this.
Okay. Right.
know
I
that.
think I see. So that's kind of like similar to finding ways to suppressing the source of noise, right?
Yes.
Am I saying it right? Okay, I see.
That's right. Yeah. So just to
Right.
get rid of the RTS noise, or to kind of push it into a regime where you could do something about it. Um, I mean, people used to kind of compete to kind of
Right.
have the lowest RTS noise possible.
Right. I see.
But I mean, that would be good for you because it then moves the experiment into a regime where your
Quantum.
system could respond in time. The
Right.
last thing you want is RTS noise at 10 gigahertz, and then there's nothing you can do about it.
Right. I see. Okay, that's a really good input. Yeah. So we hope that this work could be useful at some point where those classical techniques or the techniques to try to remove the source of noise have like limitations, and you cannot do anything anymore. And then there's still some leftover charge noise at the end, and then maybe this one could be useful. I don't know. I haven't like we haven't been able to convince any experimentalists to try this protocol yet. There are a lot of issues. I think it's not easy as far as I understand. Yeah.
I'm sure David could find someone to have a go.
Okay. Sure.
But thank you so much, Areeya. This has been a great and interesting talk. So thanks for
Thank you.
opening the seminar series this term.
Yeah.
Hope to see you soon. And for everyone else on the on the Zoom call, there will be another talk on Friday next week, which we will send out details about.